All right, silly people, here's the situation. We have a potential, which is minus alpha times a couple of Dirac delta functions. Um, and we have to find the bound state solutions for the wave functions in this potential. Um, so the standard procedure for finding a wave function is by solving the Schrodinger equation, which I'm writing out here. The 2 there, and then that's going to be equal to E psi on the right-hand side. Noticeably, V is equal to 0 in any of the 3 regions, which I've enumerated 1, 2, and 3. And so that's the whole Schrodinger equation right there. There's no potential term, really. You can continue to solve this, putting the minus 2me over h bar squared on the right-hand side, and keeping in mind the fact that the energy E is going to be less than 0 because we're looking for bound state solutions. This quantity is actually positive, so we can collect it into a wave number k squared psi, where k is going to be positive and real. So no worries about that. So standard solution for this sort of thing is going to be psi equals a e to the minus kx plus b e to the kx. But considering that we have boundary conditions, this isn't going to work for all 3 regions. And that's not even the only class of solution that we can get, because we can also get odd solutions. What I've just written down as an even solution, but we can have odd solutions to the Schrodinger equation. Psi equals a e to the minus kx, and then there's a minus sign on the positive exponent term, which we're also going to look at, but we're going to focus on the even solution right now. Actually, I have to look at the wave function in each of these regions specifically. For the first region, we have that psi 1 will just be a e to the minus kx, because if we left on the e to the positive kx, this wave function would blow up at x equals infinity, and we can't have that. So it's just this. For psi 2, we actually find that the constant is the same for both the positive exponent and the negative exponent, so we have something like that. And for psi 3, we have the same constant a for psi 1, but it's e to the kx, so it doesn't blow up at minus infinity. And so now we can look at a boundary condition where the wave function will have to be continuous at x equals a. So we have that. We can just plug in our solutions to that. So we have a e to the minus ka equals b e to the minus ka plus e to the ka. And then I'm just going to solve that for a for something that you'll see in a second. But yeah, we have that expression now relating the constants. We also have the boundary condition that the derivatives of the wave function will be discontinuous at the boundary. So you'll find that if you take the derivative of the wave function on the right-hand side of the boundary, set x to the boundary, and then take the derivative of the solution on the other side of the boundary, also set equal to a, it'll be minus 2m alpha over h bar squared times the wave function at a, which I'm just going to use psi 1 for that. So just doing those derivatives, we have minus ak e to the minus ka minus b times minus k e to the minus ka plus k e to the ka equals minus 2m alpha over h bar squared to the minus ka. I'm going to divide the equation by minus k so that it looks a little bit less stupid. It's going to be plus now. This is going to be e to the ka minus e to the minus ka equals 2m alpha over h bar squared ka e to the minus ka. And then we can plug in our expression for a, which we found from the first boundary condition. So we find that it's b e to the minus ka plus b e to the positive ka plus b e to the ka plus b e to the minus ka equals 2m alpha over h bar squared k b e to the minus ka plus b e to the ka, right? And actually, there's a minus sign on here, and that's an important thing to have because we find that actually this term cancels out this term, which is pretty funky. And then we also notice, right, that b is on all of these terms, which means b is going to cancel out in the end, which means b is a free variable. So we're going to set b equal to 1. And now we have the equation e to the ka equals m alpha over h bar squared k e to the minus ka plus e to the ka. This is a pretty hard equation to solve, but Griffiths gives us a couple of trial functions for alpha to try out on here. So he gives us alpha equals h bar squared over ma. And then this is going to be e to the ka equals minus 1 over ka e to the minus ka plus e to the ka. That's what you get for this equation when you plug in that value for alpha. And this is an equally unsolvable algebraic equation, at least not solvable by me. I did solve it with Desmos, and I found that k is just going to be 1.109 over a. And we can actually use that now to find out what the energy is, because if you remember, we defined k squared, or we defined k to be the square root of 1 minus, or square root of 2 me over h bar, and you set that equal to k. And you can just solve that for e now. So it's going to be minus h bar squared over 2m times 1.109 over a squared. So for this value of alpha in the bound state, this is your energy. But then Griffiths also gives us another alpha to try out. He was so generous in that regard. This time it's over 4ma. So e to the ka equals m alpha over h bar squared k e to the minus ka plus e to the ka is now the equation we have to solve. And that's actually going to be a over 4, haha. It's just 1 over 4 ka. That's now the equation that we have to solve. And then, again, you can't really solve this analytically, but you can get a computer to solve it for you. And I got 0.369 over a for the wave number, and then the energy will now just be minus h bar squared over 2m 0.369 over a squared. And we can actually plot these solutions, but I'm not going to do it yet. I'd rather go ahead and get the odd parity solutions for the wave function. So for that, we're going to have psi 1 equals a e to the minus kx, just like we did last time. But then the psi 2 looks different now because there's going to be a minus on the positive exponent term, right? And now this is going to be minus e to the minus, or minus a e to the kx. That way we have that the wave function is odd. And then we just kind of solve for the constants in the same way that we did before. That the wave function is continuous at the boundary x equal a, and so we have a e to the minus ka equals b e to the minus ka minus e to the ka. Then we can use that to say that a equals b times 1 minus e to the 2ka. And then do the discontinuity of the derivatives again. And that boundary condition hasn't changed. Minus 2m alpha over h bar squared a e to the minus ka. Or I guess I should write in general psi of a, right? But then actually do these derivatives now. So we have minus k a e to the minus ka minus b minus k e to the minus k a plus, or no, that's still minus k e to the ka equals minus 2m alpha over h bar squared a e to the minus ka. And then much like before, we'll divide by a factor of negative k. But it's still pretty gross because we still have a minus b times e to the minus ka plus e to the ka, right? And then this is 2m alpha over h bar squared k a e to the minus ka. But we can plug in our expression for a up there. We have b e to the minus ka minus b e to the minus, or positive ka. Haha. We have minus b e to the minus ka minus b e to the ka on that side. And then on this side we have b e to the minus ka minus b e to the minus ka. And that should do it. This time, this term cancels out this term. No, it doesn't. This term cancels out this term. Yeah. But these terms are still here. So we have that b is actually on each of these terms again. So again, b is free and we can set it to 1. But now we have this equation, which looks like minus e to the ka equals m alpha over h bar squared k e to the minus ka minus e to the minus ka. And we can actually, I'm going to actually just flip the signs on that junk. Minus e to the ka. And I'm realizing now that I'm writing this in a really goofy way. So this is going to be ka, this is going to be ka. So this is going to be ka, and it's going to be minus ka here. But that looks good now. And then let's plug in the same values for alpha that Griffiths gave us. So alpha equals h bar squared over ma. We find that the new equation that we have to solve is e to the ka equals 1 over ka e to the ka minus e to the minus ka. And I did use Desmos to solve that again. So we have 0.797 over a, and that the energy will be minus h bar squared over 2m times that number squared. And then if we use the other value of alpha that Griffiths provides, we get h bar squared over 4ma. We get e to the ka equals 1 over 4ka e to the ka minus e to the minus ka. And we get that k in this case is actually negative, which is really crazy. We have minus 0.628 over a. And so e will be minus h bar squared over 2m minus 0.628 over a all squared. Notice that even though we found a negative wave number, we still have a negative energy, which is the basis of the solutions we're looking for. So we're all cool there. Now let's actually plot some wave functions. All right, so this is a Desmos page. First of all, I'm going to show you how I actually found what values of k to use. So right here is the equation which we solved to get k in the even solution for alpha equals h bar squared over ma. And so this black line represents that equation there, and its solution at x or at y equals 0, that is the value of k, and then you divide it by a. So that's what I wrote down here. And then I constructed each of the wave functions. So in the x is greater than a region, remember we set b equal to 1, and then this was a. So we have that sort of thing. And then in the in-between region, again, we found that b was equal to 1. So we sort of just get that. And then that's the solution for the negative, or x equals minus a part. So that's cool. If we wanted to plug in a different value of alpha, like if h bar squared over 4 ma, or h bar squared, whatever. This is the equation that we solved in the second part, which has a different solution at 0.369 for k. So we just plug that into here, 0.369. And then this is what the wave function looks like with that value for alpha for the even solutions. You want to talk about the odd solutions? This gets even weirder. So for the odd solutions, we just make this negative, and we make this negative with a negative sign. We make this negative, and also this negative. Now let's talk about the first value of alpha, which has a solution at x equals 0.796 or 797. 797. So that's kind of what the wave function is going to look like. You can see it's still discontinuous at the same parts at x equals minus a and x equals a, and kind of just being freaky and odd in the way that it is. If you wanted to plug in the other value of alpha, where you have a 4 here, you find that the solution for k is again in the negative direction. So we have a negative k, which is minus 0.628 according to that solution. And we get this wave function, which is still certainly discontinuous here and here, but now we have that it's flying off into minus infinity and positive infinity on either sides of 0, which means this isn't actually a solution to the wave function. If you plug in that value of alpha, you're going to get something that doesn't work. So, I mean, just keep in mind that for the odd wave function, you need that alpha equals h bar squared over ma to have a solution that makes sense. And actually, while we're here, if you want to talk about what the limiting cases are for the energy, that is the limiting case for A is really, really small, or A is really, really big. If you let A go to 0, so let's actually change this back here to positive 797. If you make A smaller and smaller and smaller, then you find that this just ends up looking like the regular delta function potential, with it just being really small everywhere except for 0, where it's really large. So then that energy just goes to whatever the energy for the single delta function is, which is m alpha, minus m alpha over h bar squared. Okay. So that's pretty cool. No, it's minus m alpha squared over 2h bar squared. Yeah. For A approaching 0. If you make A really, really large, though, so let's make A just go to infinity, it very quickly becomes very unreadable, and now it's just a complete mess. So if we let A go to infinity, the wave function completely flattens out. We have no idea where it is, and the energy is pretty much 0. Yeah, the energy is 0 because in order for this solution to still work, it can't be greater than 0, and it's getting closer and closer to 0, so I'm going to call it 0 and be cool with that. Okay.